In just over 10 hours of test observations, a brand new telescope in the mountains of Chile found more previously unknown asteroids than most entire national observatories find in a decade. Then, months later, using nothing but its own early, unpolished engineering data, that same telescope quietly submitted over 11,000 new asteroid discoveries to the organization that tracks every object in our solar system in a single batch. And in February of this year, it began sending out alerts about changes happening in the night sky at a rate of 800,000 in one single night, a number that's expected to eventually climb into the millions every single night for the next decade. This is the story of the Vera C. Rubin Observatory, why astronomers have been quietly stunned by what it's already captured before its real mission has even fully begun, and what happens now that its 10-year survey of the entire visible universe is officially underway. If you want more real discoveries explained without exaggeration, subscribe now, because this telescope is going to be rewriting astronomy headlines for the next decade. To understand why this particular telescope has generated this level of reaction from professional astronomers, you first need to understand what it was actually built to do, because it isn't trying to be the deepest or the most zoomed-in telescope ever constructed. The Vera C. Rubin Observatory, perched at the summit of Cerro Pachon in Chile, is the result of more than 2 decades of planning, funding battles, and engineering work, jointly operated by the U.S. National Science Foundation and the Department of Energy. Its actual telescope is called the Simonyi Survey Telescope, an 8.4-meter instrument feeding into the largest digital camera ever built for astronomy, a 3.2 gigapixel sensor roughly the size of a small car. What makes Rubin genuinely different from virtually every other major telescope in operation isn't its size alone. It's the fact that it was built specifically to move fast and photograph enormous stretches of sky repeatedly, night after night, for 10 consecutive years, rather than spending long stretches of time zoomed in on a single distant target, the way telescopes like Hubble or Webb typically operate. It helps to understand just how much raw engineering went into making a telescope capable of producing this volume of data in the first place, because Rubin's approach required solving problems that had never been fully solved together on this scale before. The camera itself, built primarily at the Department of Energy's SLAC National Accelerator Laboratory, took years to design and assemble, and its focal plane alone is large enough that a single one of its images, if printed at normal photo resolution, would require roughly 400 ultra-high-definition television screens just to display in full. The telescope uses an unusual 3-mirror design that lets it capture an extremely wide field of view in a single exposure, while still maintaining sharp image quality across the entire frame. A combination that's genuinely difficult to achieve, since wide fields of view and sharp corner-to-corner clarity tend to work against each other in traditional telescope designs. Every single night that Rubin operates at full capacity, it's expected to generate roughly 20 terabytes of raw data, which then has to be processed, compared against previous images of that same patch of sky, and checked for anything that changed, all within about 60 seconds, so that alerts about supernova, moving asteroids, or flaring black holes can reach astronomers around the world while those events are still actively happening rather than days or weeks later. That mission has an official name, the Legacy Survey of Space and Time, and the basic goal is almost absurdly ambitious once you actually hear it stated plainly. Over the next decade, Rubin is going to scan the entire visible southern sky roughly every few nights, building what astronomers are already calling the greatest cosmic movie ever made, a continuous, ultra-high-definition time-lapse record of the universe, capturing anything that moves, flickers, explodes, or changes brightness across the entire sky, essentially in real time. Over the course of that decade, Rubin is expected to capture roughly 20 billion galaxies, a number that's difficult to even hold in your head properly, along with detailed information on billions of individual stars within our own Milky Way. The first real glimpse of what this telescope was actually capable of came on June 23, 2025, at a public event where scientists released Rubin's debut imagery, captured using just over 10 hours of test observations before its main survey had even formally started. One of those first images, which the observatory team nicknamed the Cosmic Treasure Chest, showed a section of the Virgo cluster roughly 55 million light-years from Earth, and contained an estimated 10 million galaxies in a single frame, itself representing only about 0.05% of the total number of galaxies Rubin expects to capture across its full 10-year mission. A second debut image combined 678 separate exposures taken over just over 7 hours of observing time to reveal the Trifid and Lagoon nebulae in extraordinary detail, showing faint clouds of gas and dust several thousand light-years from Earth that simply hadn't been visible with this level of clarity before. It's worth understanding that these asteroid totals didn't all arrive in one single burst either, and tracing how they built up over time actually tells its own story about how quickly this observatory has been ramping up. The very first handful of discoveries, just 73 asteroids, came from brief early test observations using a smaller commissioning camera back in late 2024. Essentially, a shakedown run to make sure the basic systems worked at all. Then came the first look observations in April and May of 2025, which produced the roughly 1,500 new asteroid discoveries that were folded into the headline-grabbing total announced at that June event. And then, once Rubin moved into what scientists call its early optimization surveys over the summer of 2025, still short of the observatory's final fully tuned operating mode, that same pipeline produced the batch of over 11,000 new discoveries submitted to the Minor Planet Center. Add all of those phases together, and Rubin had already contributed more than 12,700 confirmed asteroid discoveries before its official 10-year survey had even formally started, a track record that made the eventual June 30th start of full operations feel less like a beginning and more like the observatory finally being allowed to do, at scale, what it had already proven it could do in miniature. But it was what Rubin found moving through our own solar system during that same brief test period that really caught the attention of scientists who track near-Earth objects for a living. In roughly 10 hours of observations, using engineering quality data from a telescope that hadn't even begun its official mission yet, Rubin identified 2,104 previously unknown asteroids, including 7 near-Earth asteroids, none of which pose any danger to our planet. To put that number in real perspective, astronomers worldwide, using every ground-based and space-based observatory combined, typically discover around 20,000 new asteroids in an entire year. Rubin matched roughly a tenth of that annual global total in a single 10-hour test run before its actual survey had even begun. If a story built on real, verified numbers from the scientists actually running this telescope is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. Jelko Ivazic, the deputy director of Rubin's Legacy Survey of Space and Time, put that comparison in terms that are hard to forget once you actually hear them. Speaking at the event where these early results were unveiled, he pointed out that the asteroid haul from that single short test session represented roughly 5 times more discoveries than every astronomer on Earth combined had managed in the 2 centuries since the very first asteroid was ever discovered. His exact framing was that Rubin could outdo 2 centuries of collective human effort in this particular area in just a couple of years, and based on what's happened since that announcement, that prediction has already started proving itself out. Because the asteroid discoveries didn't stop with that initial test run. Roughly 10 months later, scientists at Rubin submitted a far larger batch of findings to the International Astronomical Union's Minor Planet Center, the official global authority responsible for cataloging every confirmed object in our solar system. Using data collected during Rubin's early optimization surveys, still not even the observatory's fully polished final operational mode, scientists confirmed over 11,000 new asteroid discoveries in a single submission, including 33 previously unknown near-Earth objects and hundreds of newly identified worlds orbiting beyond Neptune. 2 of those distant trans-Neptunian objects turned out to have such extreme, elongated orbits that, at their farthest points, they travel to roughly 1,000 times Earth's distance from the Sun, placing them among the 30 most distant asteroids ever confirmed by anyone. Mario Juric, a professor at the University of Washington, and the scientist leading Rubin's solar system research team, described that submission as just the tip of the iceberg, and made a point of stating plainly that discoveries which used to take years or entire decades to accumulate are now something Rubin can produce in a matter of months. The nebula image released as part of that same first look event deserves a bit more attention on its own, too, because it demonstrates a completely different strength of this telescope compared to the asteroid haul. Rather than a single quick exposure, that image of the Trifid and Lagoon nebulae was built by carefully stacking 678 separate shorter exposures on top of one another, a technique that lets extremely faint details, light so dim it would be completely invisible in any single frame, gradually emerge once enough individual images are combined and averaged together. That's part of how Rubin was able to reveal delicate structures within the clouds of gas and dust making up those nebulae with a level of clarity that hadn't been captured before at that particular combination of scale and depth. It's a preview of exactly the kind of processing Rubin will be doing constantly across its entire 10-year survey, not just for pretty pictures of nebulae, but for detecting the faintest, most distant galaxies and the subtlest gravitational distortions in their shapes that scientists need in order to actually map dark matter's influence across the universe. None of this has come without real engineering headaches along the way either, and it's worth being upfront about one challenge in particular that Rubin's team has had to actively work around. The rapidly growing number of satellites in low Earth orbit, used for things like global internet service, can leave bright streaks across long exposure astronomical images, and Rubin's extremely wide field of view makes it more likely than most telescopes to catch one crossing through any given frame. Engineers on the project have had to build specific software techniques to identify and remove those satellite streaks from the data without accidentally erasing something scientifically real, like a genuine asteroid or a fast-moving cosmic event, sitting in roughly the same part of the frame. It's an ongoing and evolving problem rather than one that's been fully solved once and for all, and it's one of several practical complications the Rubin team has had to manage quietly behind the scenes while still producing the kind of results that keep making headlines. If you found these numbers as staggering as I did while researching this, drop a comment letting me know. It genuinely helps me figure out what to cover next. Asteroids are only one small slice of what this telescope is actually designed to catch, though, and this is where Rubin's second major milestone comes into the story. Once Rubin reaches its full operating rhythm, scientists expect that nightly alert total to climb as high as 7 million every single night for the next 10 years. Each of those alerts flags something that changed in the skies compared to Rubin's previous pass over that same patch. A newly discovered asteroid on the move, a distant supernova suddenly flaring to life, an active galactic nucleus, essentially a supermassive black hole at the center of a galaxy, brightening as it feeds on surrounding material, or a variable star pulsing in brightness in a pattern astronomers hadn't previously mapped in that much detail. Luca Rizzi, a program director at the National Science Foundation, described what this actually means for working scientists in fairly direct terms, explaining that by connecting researchers to this kind of vast, continuous stream of information, Rubin makes it possible to follow events in the universe as they're actually unfolding in real time, from the most explosive and dramatic all the way down to the faintest and most fleeting changes that would have simply gone unnoticed by any previous generation of telescope. That alert stream milestone set the stage for what happened next, because on June 30th of this year, Rubin Observatory officially began the real thing, full science operations, for its actual 10-year legacy survey of space and time. Everything before that date, the first look debut images back in 2025, the engineering data that produced 11,000 asteroid discoveries, the alert stream switching on in February, had all technically been preparation, commissioning work, and controlled testing ahead of the observatory's true operational mission. As of that date this past June, Rubin is now actually running its intended survey, systematically imaging the entire visible southern sky over and over every few nights for the next decade, exactly as designed from the very beginning. It's worth pausing here to understand why Rubin is named the way it is, because the choice wasn't incidental. The observatory honors Vera Rubin, an American astronomer whose work in the 1970s and 1980s provided some of the most compelling observational evidence ever gathered for the existence of dark matter, the mysterious, invisible material that appears to make up roughly a quarter of the entire universe's mass and energy content, detected only through its gravitational effects on visible matter, rather than through any direct observation of the material itself. Rubin's original research focused on measuring how fast stars orbit within spiral galaxies, and she found something that shouldn't have been possible if those galaxies only contained the visible matter astronomers could actually see. Stars far from a galaxy's center were orbiting just as fast as stars closer in, a pattern that only made physical sense if an enormous amount of additional unseen mass was distributed throughout the galaxy, holding everything together gravitationally. That observation became one of the strongest pieces of evidence supporting the existence of dark matter, and naming this specific observatory after her carries real weight because studying dark matter and its equally mysterious counterpart, dark energy, sits at the very center of what Rubin's 10-year survey is actually designed to help scientists finally understand. That broader scientific mission is worth spelling out clearly because the asteroid discoveries and the dramatic debut images, as impressive as they are really just the most immediately shareable pieces of a much larger scientific undertaking. Over its full 10 years of operation, Rubin is expected to help researchers map the structure and distribution of dark matter throughout the universe by studying how its gravity subtly bends and distorts the light of distant galaxies passing near it. It's expected to track the effects of dark energy, the mysterious force that appears to be accelerating the expansion of the universe itself, by precisely measuring the positions and behavior of billions of galaxies scattered across cosmic time. It's expected to build the most detailed map of our own solar system ever assembled, expanding our current catalog of roughly 1 million known asteroids toward an eventual total that could reach 5 million objects within just the first few years of full operation. And, because Rubin sweeps across such enormous portions of the sky so frequently, it's also expected to become, according to researchers involved with the mission, the single most effective observatory ever built for catching interstellar objects, The rare visitors from other star systems like Oumuamua, Borisov, and the more recently studied 3I Atlas passing through our own solar system, often catching them earlier in their approach than any previous survey system managed to. So what does all of this actually add up to? In less than 2 years since its very first test observations, a telescope that hasn't even completed its opening chapter of operations has already reshaped how quickly humanity can catalog the objects moving through our own solar system, has already begun issuing hundreds of thousands of real-time alerts about changes happening across the night sky every single night, and has now formally begun a 10-year mission specifically designed to help answer some of the largest unresolved questions in all of modern physics: the true nature of dark matter and dark energy, the structure and history of our own galaxy, and the full inventory of everything moving through our own cosmic backyard. What makes the next few years genuinely worth watching closely is that almost everything covered here still technically counts as Rubin warming up. The asteroid totals, the alert stream numbers, even the debut images themselves were all produced using data the observatory's own team openly describes as early, engineering grade, and not yet representative of its fully tuned performance. Scientists involved with the project have been fairly direct that the real scientific harvest, the detailed maps of dark matter's distribution, the precise measurements of how the universe's expansion is accelerating, the full multi-year record of billions of galaxies changing brightness over time is still ahead, built up gradually as the same patches of sky get revisited again and again over the coming decade. Astronomers who spent their entire careers working with data trickling in one discovery at a time are now describing a genuine shift in how the field itself works, where entire subfields of research that used to advance one careful measurement at a time are now expected to be reshaped within a period of just a few years. It's also worth placing Rubin in context against the research it's directly building on, because this isn't the first attempt to measure dark energy's effects on the universe's expansion. For years, cosmologists relied heavily on projects like the Dark Energy Survey, an earlier effort using a smaller telescope that mapped hundreds of millions of galaxies over roughly 6 years of observing time to study the same fundamental questions Rubin is now tackling at a dramatically larger scale. Researchers who worked on that earlier survey have described Rubin as the natural next step, a way of taking techniques and lessons refined over the past decade and applying them across a far larger volume of sky, far more frequently, with far more sensitive instruments than were available before. That continuity matters, because it means Rubin isn't starting from scratch scientifically. It's inheriting an entire generation of accumulated expertise in how to actually extract meaningful answers about dark matter and dark energy from enormous catalogs of galaxies, and then applying that expertise to a dataset that dwarfs anything cosmologists have ever had access to before. If stories like this, grounded entirely in verified data, straight from the scientists actually running the mission, are what you come here for, subscribe to this channel and turn on notifications, because Rubin has barely started its real 10-year survey. And there's a very real chance the next set of results makes everything covered here look modest by comparison. Thanks for watching, and I'll see you in the next one.